Hello students, and welcome to our lesson on an introduction to graphs and linear equations. What we're going to be doing here is introducing the rectangular coordinate system, plotting some points on it, and then connecting the dots between, literally connecting the dots, that'll take us from a sequence into a linear equation. So in the previous topic, we saw arithmetic sequences. Now we're going to be doing linear equations, which is just going to take a sequence and draw a line through the dots that it creates. So again, literally, we're going to be connecting the dots today. All right, let's get started with the rectangular coordinate system. This is what allows us to graph points and represent data in a visual graphical manner. The rectangular coordinate system is formed by two number lines that intersect at right angles. So you can see we have the y-axis is this vertical number line, and the x-axis is this horizontal number line. When it says they intersect at right angles, notice it looks like an addition symbol, a plus sign, where there is a box, okay, 90-degree angle where these intersect. The horizontal number line I said was called the x-axis, and the vertical number line is the y-axis. Very important we know the difference between x and y, because when we plot points, we're going to need to know which one is which. Together, the axes divide the plane into four regions, and these are called quadrants. They're called quadrants because quad means four, right? Now you can see them labeled on the graph over there. In the top right, we have quadrant 1. Notice these are Roman numerals, so that's a capital I. Then we go counterclockwise to go to the next quadrants. So top right is quadrant 1. Then in the top left, we have quadrant 2. Bottom left, we have quadrant 3. And bottom right, we have quadrant 4. And then we just restart back at 1. So now, plotting points on these graphs. A point is named by what is called an ordered pair, which is x comma y. X is going to be the horizontal coordinate and y is the vertical coordinate. So the ordered pair x comma y is going to tell us how much to go to the side and how much to go up or down. The axes intersect at the point 0, 0, and we call that the origin. Okay, so now when we look back at this coordinate plane up here, where those lines cross right in the center, that is the origin, the point 0, 0. It means that you start right here at the center where these axes cross, and you do not go left, right, up, or down. You just stay right there at 0, 0. Now, the reason I describe it that way is you don't go anywhere, left, right, up, or down, is because for every other point other than the origin, we will go left, right, up, or down. So our next bullet is to plot an ordered pair, x comma y. We're going to move x units either left or right from the origin, and then move y units up or down, where specifically we will be going to the left if x is negative and to the right if x is positive. Then for the y direction, we will go up if y is positive, but down if y is negative. So because these are number lines that make it up, we know that on the x-axis, so up here, the left side is the negative direction and the right side is the positive direction. So if x is negative, you go to the left, and if x is positive, you go to the right. Similarly, the y-axis is a number line where down is the negative direction and up is the positive direction. So now let's go ahead and put that into practice, as well as just making sure we understand which quadrant is which and how we can easily tell what quadrant we're in just by looking at the ordered pair. So we have 6 different points we're going to plot here. We're going to plot each point on the graph and state which quadrant it lies in. If it lies directly on one of the axes, then we just state that it lies on that axis and we name the axis, either x or y. If it's the point 0, 0, then that's just the origin. So we would call it the origin. Okay, but otherwise, if it lies entirely in one quadrant, we name it with that quadrant. So first one, we have 3 comma 4. Just to be clear, this is an ordered pair where x is 3 and y is 4. So now, in order to put this on the graph, once you get good at this, you're going to be able to just look and go, oh, 3 to the right, 4 up, and you're going to be able to put a dot right there. But for the first couple ones we do here, I want to really make sure we understand why this is called the rectangular coordinate system. Okay? Every point we plot makes a rectangle, where in order to plot that blue dot I put on the graph at 3 comma 4, what I had to do was go to the right by 3 units and then go up 4 units. So now notice, if I do that in the other direction, if instead I go up by 4 and then I go to the right by 3, do you see how all those red lines form a rectangle? Okay, and that is exactly why we call it the rectangular coordinate system. Every point is really just a rectangle where the x value is the width of the rectangle and the y is the height of the rectangle. So then all we're doing is positioning these rectangles to get the point to where we need it to be. So anytime you see a point, just remember you're not moving diagonal by 3 or 4. You're moving left or right by 3 and up or down by 4. Okay, where positives here tell me to go in the positive direction for both, which meant to the right and up. So I end up with that blue dot there. And I'm going to go ahead and instead of putting solid lines here, because I want to be able to leave these up as we do the rest of the problems, I'm going to draw some little dotted dash lines that form that rectangle. That way we know where that blue dot came from. So again, we went to the right by 3 and we went up by 4. So now that one is in the top right quadrant. So that is going to be QI, which stands for quadrant 1. Okay, we use that Roman numeral I and a Q for quadrant. Now, number 2, we have x is -2, y is 5. That means that I'm going to go 2 units to the left and 5 units up. So on my coordinate plane, I'll do these dots in green. We're going 2 to the left and then 5 up. So when I put a dot right there, oh, I only went 4 up. Let me go up one more, 5 up. So that point right there is going to be -2, 5. And real quick, I'm going to label the other one was 3, 4. And all I had to do to get to that -2, 5 was go 2 units to the left and 5 units up. Okay, where because it was a -2, that's why I went left. Okay, but the distance, remember we talked about absolute values in this class, distance was +2. But because it's a -2, that meant 2 units to the left. All right, so now we are in the top left quadrant. So that is Q2 or quadrant 2, QII, okay, for quadrant 2. Okay, so now we've done 2 of these so far. I can tell you what quadrant these are in without graphing them. The first one was 3, 4. It was positive and positive. That means I'm going to go right and up. So that's quadrant 1. For the second point, -2, 5, that told me that I was negative and then positive for the x and y. So that meant I was going to go left and then up. So that's always going to be quadrant 2. So for the third one now, we have a negative and a negative, -4, -3. That means I'm going to go 4 left and 3 down. So notice I'm in quadrant 3 now down here. So you can tell which quadrant they're in just by which values are negative between x and y. So for this one, -4 means 4 left, and then -3 means 3 down. So I can go ahead and label my point here, -4, -3. And we can say that that is in Q3 or QIII, quadrant 3. Next one, number 4, says 5, -1. Notice that it's a positive x and a negative y. For a positive x and negative y, I'm going to end up in quadrant 4. I'm going to go 5 units to the right and then 1 unit down. Okay, so that puts me over here at 5, -1. So because we are to the right and down, we are in Q4, which is QIV. Okay, if you haven't worked with Roman numerals before, IV, V means 5, and when you put an I in front of it, it means 5 minus 1, which is 4. So the number 4 in Roman numerals is IV. All right, now we have 2 more that are special cases where we're going to be on an axis. Number 5 is 0, 4. The 0 means we do not go left or right at all, but the 4 means I'm going to go up 4. So I'm going to have to draw my label a little to the side here, but 0, 4 is right there, and that is on top of the y-axis. So instead of naming a quadrant, we'll just say that it's on the y-axis. And then number 6 is -3, 0. That means to go 3 left, but do not go up or down at all. So 3, 0 is going to be right there on the x-axis. And again, the only other case we might have is if the point is 0, 0, that is the origin, okay? It is in none of the quadrants. It's on both axes. Technically, it's in all 4 quadrants, but we just call that the origin for simplicity. All right, so that was plotting points. Now we got to connect the dots between arithmetic sequences and what we're really trying to get to, which is linear equations. So when we want to visualize an arithmetic sequence, it's going to start to connect the dots between what a sequence is compared to an equation. So a graph allows us to display the relationship between inputs, which are x values, and outputs, which are y values. Arithmetic sequences can be graphed by thinking of the term numbers as the x and the term itself as the y. So for example, if I have that a naught is equal to 7, then I can turn that into a coordinate that I can graph by thinking of a naught, that term number is 0. So I'm going to make 0 my x value, and then make a naught itself, the 7, be my y value. So if a naught equals 7, I can graph the point 0, comma 7 to represent that. Where again, the input is the term number. So if you tell me which term you want me to graph, okay, that's my input. And then I can tell you what the value of that term is. That's the output. So now, number 7 says to write the explicit rule for an arithmetic sequence modeling the situation here. Sarah starts with $10 in her savings and adds $1 every day. In the previous topic, we saw that 10 here would be our A naught, our initial term, and that adding $1 per day, that is our D value. So now when we write the explicit rule, we can go ahead and say that A sub n is equal to A naught plus n times D. So if we plug in our two values here, we can say that A sub n equals 10 plus 1 times n, okay, or n times 1. Now, because the D value is 1, n times 1 is a little bit unnecessary, but it means exactly what we need it to mean. If we wanted to, we could rewrite it as A sub n equals 10 plus n, where we don't write that 1 there, but it's not actually going to make a difference for our purposes here. So what we needed to know is that we need to do 10 plus n, okay? So we have our initial term is 10, and our common difference is 1. Now let's use this to construct the next few terms in the sequence. So number 8 says let x represent how many days Sarah has been saving for, and y represent how many dollars she has in her savings. The table below models the first 4 days of her savings, and then we're going to graph these points. So in the table, we see that we have a column for x, which we're told is the number of days. We have a column for y, which is the amount of money she has in her savings. And then we have ordered pairs, which just take the x and y and put them together as an ordered pair. So now let's real quick see how this connects to our sequence description up above. Okay, we said at the very top of the page that we can think of the term number as the x. So in our table here, when it says x days, that is the n value that we're using in our sequence. So x days, this really represents n. And then y is the savings. That is going to represent the actual value of the term, so that's a sub n. So what we're given here is that when x is 0, that means we're looking for term 0, okay, which is our initial term. We know that our initial term was $10, so a sub 0 should just be 10 in the table. And notice right here, that's what we have. We have 0 for our n and 10 for our a sub 0. Then our common difference is 1. So when we save for 1 day, Sarah's savings goes from $10 to $11. It goes up by 1. When we save for 2 days, it goes up by 1 again to 12, and then 13, and then 14. Okay, so this is just the first 5 terms of the arithmetic sequence that we wrote up above. Now what we're going to do is graph these ordered pairs over here on the right, where all we did was take the n value and the a sub n values and write them next to each other as x comma y. So we can go ahead and graph these just like we were graphing before, where notice that I only have quadrant 1 shown on my coordinate plane, because when we graph a sequence, we start at 0 and we go in the positive direction in this case. So all of my values are going to be in quadrant 1. So I don't actually need the other 4 quadrants to be drawn here because we're not going to use them. If I wanted to, I could technically extend my graph in every direction, to include all 4 quadrants. But if we know we're not going to need them, then why bother drawing them, all right? So let's graph these points. First point is 0, 10. So I'm going to go no units left or right, but I'm going to go 10 units up from the origin. So that point is right there, 0, 10 up here. Then we're going to 1, 11. So 1, 11 means from the origin, go 1 unit to the right and 11 units up. So we're going to be just slightly up and to the right of my previous dot. Then we have 2, 12. So I go 2 units to the right and 12 units up. It's going to put our dot right there. And then 3, 13 is up and to the right one more. And 4, 14 is up and to the right one more time. And that's all there is to it. We now have a visual representation of Sarah's savings, where what we're going to be doing as we move forward is turning this into a linear equation, where notice that the savings are going up each time, right? You can see these dots are moving upward. So if I drew a line through them, you could start to imagine that that line's just going to keep going up and up and up. So if Sarah keeps saving like this, eventually this will be a real big number in her savings. It'll take a while, but eventually it's going to keep going up, and it'll keep going up for forever, presumably, as long as she stays on track with her savings. But all right, that's just an arithmetic sequence. We're not quite at a line yet. So let's see how to go from a sequence to a linear equation. So linear equations follow the same pattern as arithmetic sequences, where you're adding a common difference each time. But the big difference is that sequences are called discrete points, which means isolated dots. So if you notice in my graph up above, all I did was put dots on the screen. I didn't connect anything. Linear equations, on the other hand, are not discrete. Linear equations are continuous, meaning you have to connect the dots. So linear equations are continuous and form the lines that connect those points. So we are now connecting the dots in order to make linear equations. But the way we get there is the same. We still plot the points first, and then we just draw a line through them. The common difference D, when we write a linear equation, is going to be referred to as slope, which is m. And then the initial term, a naught, or a sub 0, is going to be referred to as the y-intercept, which will be the letter b in our formula. Okay, so slope is the common difference, that's m, and b is the y-intercept, that's a sub 0. We will talk more about y-intercepts later on in this class, but for now, you just need to know that the y-intercept occurs where x is 0. So I'm going to make a little note right here that the y-intercept is when x equals 0. So this is the place where the graph touches the y-axis. So in our previous graph, you can see that our initial term there, 0, 10, that is our y-intercept. And so that's why we're saying that a naught is the y-intercept, because that's true. A naught happens when we plug in 0, and that's exactly what a y-intercept means. So now, if we look at the formulas, what we have here is the explicit formula for an arithmetic sequence. A sub n equals a naught plus n times d. And this is supposed to be the same as y equals mx plus b, which is the slope-intercept form of a line. And slope-intercept form is what we're going to use the most. So we like slope-intercept form. So let's real quick see how to relate these. Earlier, we had the formula a sub n was equal to 10 plus n times 1. So 10 plus n. I won't even write the 1 there because we already know how to simplify it. So if a sub n equals 10 plus n, and we're told that a naught right here, which is the 10, is the same as b, then I can go ahead and take this 10, put it where that b is. And we're also told that the d value is the same as m in this formula. Then I can go ahead and put a 1 where that m is, because remember, I didn't write the 1, but there's a 1 there attached to our n. So then filling in the rest of the formula, we have y equals 1 times x plus 10. So we can simplify that to just be y equals x plus 10. So the equation of our linear, or of our line, is just going to be y equals x plus 10. And that's exactly the same as saying the sequence a sub n equals 10 plus n times 1, or just 10 plus n. So notice not much changed. A sub n is now the letter y. 10 is still just 10, it's just in a different place in the formula. And n became x. So what we're doing, just like what we did in this table, is we're replacing n with x, and we're replacing a sub n with y. But otherwise, the key information, the 1 that is the common difference and the 10 that is the initial value, stays there. We do not lose those things when we convert to a linear equation. All right, so now moving on, let's go ahead and learn how to actually graph a line. As we move forward in this class, we're going to learn a few different methods for graphing a line, but those are going to be in future lessons. Today, we are going to graph lines purely by plotting points and connecting the dots. So the way we're going to do this is just like how we had a table of values for the arithmetic sequence on the previous page, we're going to make a table of values for each linear equation. So we are going to choose several inputs, which are x values. We have to choose at least 2 because a straight line requires a minimum of 2 points. We're going to compute the corresponding outputs, which are y values, and we're going to do that by using the equation provided for the linear equation. And then we will plot the ordered pairs, x comma y, on the coordinate plane, just like we did before. And then finally, we'll connect the points with a straight line, and we'll put arrows on each side of the line. So something like that one there. So number 9, we will graph the line y equals 2x plus 1. What I have in the table here is the x values that I want us to input, which are -2, -1, 0, 1, and 2. We don't have to use those x values, but for this lesson, I'm predetermining which ones we're plugging in. So now what we're going to do is just substitute in each x value for x in the formula on the right side. So if you recall, we've been doing this all semester, plugging in these x values. So this is nothing new for us. When we plug in -2 for x, I'm just taking that -2, putting it where the x is. So I will have 2 times -2, that's -4, plus 1 gives me -3. Then I'm going to, for the next row, so now I'm moving on to this one, I'm going to plug -1 in for that x value. 2 times -1 is -2, and -2 plus 1 is -1. Now when I plug in 0 for that x value, I have 2 times 0 plus 1, which is just 1. And now I want you to notice the pattern. Okay, we went from -3 to -1 to 1. If I asked you to find the common difference between these, you would say that to go from -3 to -1, all we had to do was add 2. And to go from -1 to 1, we add 2 again. And notice the formula was y equals 2x plus 1. So this common difference here is exactly the 2 that's in the formula. Okay, and we call that slope now, which we will talk more about slope in a future lesson. But just know that our common difference and the slope of the line are the same thing. So now to get the other 2 x values, or sorry, the other 2 y values, I don't actually need to plug in 1 and 2 for x. I can just use my common difference to keep going here. So to go from 1 to the next x value, I just add 2, and that's going to give me 3 here. And then if I add 2 again, I'll get 5. And now I have plenty of values that I can go ahead and plug in. So now if I write these as ordered pairs, we have -2, -3, -1, -1, 0, 1, 1, 3, and 2, 5. In order to graph this line, I could graph all 5 points, but we only actually need to graph 2 dots in order to connect them with a line and have it be accurate. So what I prefer to do is either choose the 2 most convenient coordinates or choose the 2 that are farthest apart. So I'm going to graph this top one and this bottom one. -2, -3 means go left by 2 and down by 3. So I'm going to go left 1, 2, down 1, 2, 3. Put a dot right there. And then for +2, +5, I'm going to go right 2 and up 5. Just put a dot right there. And then now all I have to do is connect my dots with a line and put an arrow on each side to represent that that line keeps going in both directions. Okay, we plugged in x values -2 to +2, But that line is not going to stop just because we didn't plug in more x values. That line keeps going forever and ever. So now that we've done that, notice I only graphed 2 points, but I have the line. So now let's see where these other 3 points would fall on this line. Okay, if I graph -1, -1, that's left 1, down 1. Do you see how that blue dot is on the black line? And then 0, 1, that's not left or right at all, just up 1. That's also on the line. And 1, 3 is right 1, up 3. That's also on the line. So the reason we can choose any of the 2 points and then draw a line through them is because they are all on the same line. So we don't need to graph all 5. We just graph whichever ones are most convenient for us to then draw a line through. All right, let's try it again. This time we're going to graph the line y equals -3x plus 4. So the first thing I'm going to do is plug in my first x value, which is -2. When I plug -2 in for this x, -3 times -2 is +6, plus 4 gives me 10. So now I'm not going to plug in any more x values. Instead, I'm going to use the common difference to go to the next terms. So I know that my common difference is this -3 right here. Okay, that's why it's in the formula. That -3 is the slope, but it's also the common difference of the arithmetic sequence. So I can use that to go up to the next term. So if I just do -3 from my 10, that'll take me to 7. -3 again takes me to 4, and then 1, and then -2. So I don't have to keep plugging in x values. I can just use that common difference. Now my ordered pairs are -2, 10, -1, 7, 0, 4, 1, 1, and 2, -2. I can go ahead and graph whichever ones of these I want. Okay, so I just need to use 2. My recommendation though is always choose the 2 that are farthest apart, but still fit on your graph. So notice all of these are going to fit on the graph. So we could graph all 5. I'm just going to do the highest one and the lowest one. Okay, and the reason you want them to be far apart is that way when you draw your line, you catch all the ones in the middle by drawing a line through them from the first one to the last one. So -2, -10 means 2 left, 10 down. So we're way down at the bottom of this graph. And then +2, -2 is going to be right. Oh, wait. Whoa, Mr. K, what did we do there? That dot's in the wrong place. -2, 10. I went left 2, down 10. That's wrong. We need to go left 2, up 10. So left 1, 2, and then up all the way to 10. So we're going to be at the top of that graph instead. Sorry about that, team. So now, next one is +2, -2. That means right 2, down 2. I can put a dot there. And now because I have 2 dots, I can go ahead and connect them. And all my other points should fall in between these 2 dots. So if I go ahead and test, -1, 7 would be left 1, up 7. That's on the line. 0, 4 would be not left or right at all, just up 4. That's on the line. And 1, 1 means right 1, up 1. That's on the line. So those blue dots are always going to be on the same line as the 2 red dots because they all come from the same equation. All right, so now, last thing we're going to talk about in this one is scaling a graph. Notice these 2 graphs both go from -10 to 10 on both the x and y axis. That's because I gave us convenient things to graph. But that's not always going to be the case, okay? Sometimes you're going to graph things that just don't look that nice. And so what we need to do in that scenario is rescale the graph. So notice the graph on the screen now, the x-axis goes from 0 to 4, but the y-axis goes from 0 to 30. Very different than both going from -10 to 10. Okay, so we're going to have to take a little bit of a different approach here. So the bullet points at the top are just going to be guidelines, and then I'm going to talk a little bit more as we do the examples about how we actually do this in reality. So top bullet point, since it is common to graph both large and small values, the ticks, okay, the little marks on the graph do not have to be equal to 1. So in the previous graph, let me go back a page, every little box on this graph was worth 1. It was a 1 by 1 box. So in order to go from 0 to 5, I go 5 boxes to the right. But that doesn't have to be true, okay? We can make the tick marks worth whatever we want. So if you see this graph down below now, When we go up 1, 2, 3, 4, 5 ticks, that takes us to 10, not to 5, which means each one of these tick marks is worth 2. It goes 2, 4, 6, 8, and then 10. And that's perfectly fine. Okay, we can make the tick marks worth whatever we want them to be. Okay, we just want to make sure that our graph will fit appropriately. So what we want is that the scale of our graphs to be convenient for including all of our important coordinates. And when I say important coordinates, sometimes you don't know what's important and what's not, so you get to decide what's important. But as you move forward in mathematics, usually the things we care about are where something starts and ends, or where it changes direction. So for us right now, we're only graphing straight lines, so they don't change direction. But think about when we were doing arithmetic sequences, we want to know where we start, and then we want to see the direction it's going, the common difference. So how that translates to what is an important point is we want to be able to see the x and y intercepts of our graph. So you always want to scale your graph so you can at the very least see the x and y intercepts. But again, as you move forward in mathematics, what is important will change. So just base it scenario to scenario. You got to make a new decision every time. All right, so now this next bullet point is really just a guideline. It says to scale an axis, find the range of your data, which is how far spread out is your data. So from 0 to what? How far do we go? So find the range of your data and divide by however many major steps you want, and then round up to a multiple of 1, 2, 5, or some power of 10, which would mean 10, 100, 1000, so on and so on. Okay, so now what does that mean? All right, well, real quick, let's do the next bullet point. It says minor steps can be used to evenly divide major steps and make the graph easier to read. All right, what is a major step? What is a minor step? Where did any of this come from? So let's look at the graph here. We have our y-axis is going from 0 to 30. Do you see how only the 10, the 20, and the 30 are labeled? So wherever we have a label and we have this kind of darker line going across the screen, that is referred to as a major step. Okay, the ones that are labeled are major steps. But in order to make the graph easier to read, oftentimes we put these lighter lines in between. Those are called minor steps. Okay, where they're not important enough to get their own label, but we still want to draw them. You know, think of graph paper, how it has lines all over the place. It just makes it easier to understand where things are because it puts a nice straight line on the page for us. So minor steps are the ones that are not labeled. Major steps are the ones that are labeled. Okay, so we got that clear. But now it says to divide the range of your data by however many major steps you want. Notice it says want, right? So that's a decision you get to make. When we look at the graph down below, there's 1, 2, 3 major steps on the y-axis. But if we look at the x-axis, there's only 1, 2 major steps. So it doesn't even have to be the same all the time. You get to decide how many times you want to divide up your graph and label a major step. Okay. So now when it says to divide by however many you want and round to a multiple of 1, 2, 5, or 10, this really is just a guideline. So I'm going to talk more about this 1, 2, 5, or 10 part in a second, but first we got to start number 11. So number 11 says, make a table showing the first 4 terms of the sequence described, and then plot the terms on the graph as ordered pairs, n comma a sub n. So we are given that a naught is 8, and the common difference d is 6. So when I fill in this table, where it says n equals 0, a sub n is 8, because that is my initial term right here. And then it tells me my common difference is 6, so to go to the next term, I just add 6 each time. So term number n equals 1, so a sub 1 is going to be 14, because I just add 6, then 20, and then 26. If I write these as ordered pairs, I have 0, 8, 1, 14, 2, 20, and 3, 26. Okay, so now we can talk about the range and the major steps. My data starts real low at 8 technically, and goes up as high as 26. Whenever you guys are graphing things, I want you to start at 0 and then go up to whatever the biggest number is. So we're going to say that our range is from 0 to 26, meaning our range is 26 units big. Okay, so I'm going to say range equals 26. Now, I want to reiterate, these are guidelines, okay? You get to make graphs how you want in general, as long as they're accurate. This is a guideline. All right, so my range is 26. Let's say I want 3 major steps. Okay, so if I want 3 major steps, so I'm going to say majors equals 3. What I'm going to do is just divide 26 by 3. And that is going to be equal to, if you divide 26 by 3, that's almost 9. So I'm going to say that this is approximately 9. Okay, it's 8 and some change. Now, what our bullet point says is to round up to a multiple of 1, 2, 5, or a power of 10. If I choose to round up to a multiple of 1, that means that I would round this nowhere. I would just keep it at 9. Okay, and then if I do that, every tick mark that I make, every major tick, instead of going up by 10 right here, it'll go up by 9 each time. So it'll be 9, 18, 27. That is okay. You can do that. All right. But what I'm going to urge you to do is instead try to round up to either a multiple of 5 or a multiple of 10. In most cases where your numbers are kind of big, that'll be better. So instead of rounding to 9 here, we're going to say that this is about 10. Okay, I'm going to round up to a multiple of 10. And that is why my tick marks here go up by 10 each time. 10, 20, 30. When I do it for the x-axis, notice it just goes from 0 to 4. Well, my actual data goes from 0 to 3. And so if I divide the range there, which is 3, by the number of tick marks I want, so let's say I want 2 tick marks here, I would do 3 divided by 2, which equals 1.5, and then round that up to be a multiple of 2, which is just 2. So then my x ticks go up by 2 each time. So I go from 0 to 2, and then 2 to 4. Just guidelines, guys. Okay, just keep that in mind. You're allowed to use whichever scale you want as long as you fit your data. These are just guidelines. In this class, I'm going to be giving you the graphs already labeled like this with these scales here. Because what normally happens in real life these days is when you pull up a graphing calculator, let's say something like this, see how the graphing calculator already has the tick marks labeled 5, 10, 15, 20 in those directions? And if I pinch the graph and zoom it a different way, see how it rescales the tick marks? So now they go up by 20 each time. And if I try to pinch it the other way, I can make it go up by 100 each time. If I hit the little house icon, it'll zoom back in and make it go up by 5s again. So technology these days kind of takes care of all the scaling for us. So the more important skill for us is we need to know how to put the dots on the graph. So the scaling part is not that important for us anymore, but we need to know how to understand the scale when we see it. All right, so we need to graph these 4 points, 0, 8, 114, 220, and 326. So all we have to do is make sure we follow along with the actual graph tick marks here. So in order to graph 0, 8, I'm going to go left or right, nowhere, but I'm going to go up 8. So I need to know where is up 8, because 8's not labeled up here. So I need to find 8. So because it goes from 0 to 10, and there's 5 tick marks in between, 10 divided by 5 is 2. So I know this goes up by 2's each time. So 0, 8 is going to be right there on the y-axis. Then my next point is 1, 14. Well, where is 1 on the x-axis? We go from 0 to 2 to 4. So 1 needs to be halfway between 0 and 2. So that means 1 is right here in the middle of 0 and 2. And so that means in between it, this box right here would be 0.5, and the box on the other side would be 1.5. So each box is only worth 0.5. Okay, I need to know that in order to know where to put the point 1, 14. All right, but now that I have that down, 114, I have 1 labeled. 14 is going to be up 7 boxes because each box is worth 2. And so 714 is right there. Now 220, both of those are labeled. So I can go directly to where the labels are for 2 and 20. Write 2 up 20, takes me to that spot. And then 326, I have to go 2 boxes to the right because remember each box is worth 0.5, and then go up 3 more boxes because each box is worth 2. And so 326 is right there on the graph. But notice the pattern. If I were graphing a linear equation, I could just connect these dots to make a straight line. So when you're graphing an arithmetic sequence, that should always be true, that your dots form a straight line. They all go in the same direction. All right, now let's try this again, but this time it is a linear equation. We want to graph the line y equals 20 minus 5x by making a table of values for -2 to +2 and then plotting the points. So the first thing we're going to do is just find all these coordinates. When I plug in -2 for x, so if I take the -2 and put it right here for x, -5 times -2 is +10, and 20 plus 10 gives me 30. Okay. Now I'm going to use my common difference to go to the next term, which is this -5 here. Okay, the slope and the common difference are the same, so I'm going down by 5 each time, which means I'm going to get 25, and then 20, and then 15, and then 10. So my ordered pairs are -2 30, -1 25, 0 20, 1 15, and 2 comma 10. So now you can see that the graph is already scaled for us, but let's just kind of try to figure out where did these decisions come from. So my data goes as high as 30. So if I want, let's say, 2 major tick marks here, what I can do is take the number 30, which is how spread out my data is, and divide it by 2. This gives me 15. And then 15, if I round up to a multiple of 10, the next multiple of 10 is 20. So I decided to use tick marks where I go up by 20 each time here. Now again, you could have gone up by 15 each time. So I could make this a 15 and this a 30, and I would still be able to fit all my data. So this is a decision you have to make. Just like when you look at the graphing calculator eventually, you can pinch and zoom this graph however you want because you're the one looking at it. So it's okay, right? You get to decide the scale here. So now when we graph these, we just got to make sure we go to the right spots. So I'm going to graph -230 and 210. -230, I can see -2 on my x-axis, and then 30 is not labeled, but it should be halfway between 40 and 20. So 30 should be right there, -2 right there. So I can go ahead and put a dot at where -2 comma 30 should be. Then similarly, 2 comma 10, I go to the right side where 2 is, okay, over here, and then 10 should be halfway between 20 and 0, so right here in the middle. So where those lines meet, I go ahead and put a dot. That right there is 2 comma 10. And then all I have to do once I have my 2 dots is just draw a line through them and put an arrow on each side to represent that it keeps on going. And then if we want to double check, we can go ahead and see that each of our other points fits on this line. -125 would be that red dot. 0 20 is on the y-axis, that's our y-intercept. And 115 is in between 0 20 and 210. All right, guys, what we're going to be doing in the next couple lessons is just learning 2 other ways to graph. We're going to be talking about slopes and then talking more about x and y intercepts. So if the terms slope and intercept didn't sit well with you yet, that's okay. We're going to talk more about it. What you really need to be understanding from this is how to plot the points. Okay, plotting the points is everything when it comes to this lesson. All right, I will catch you guys on the next one.